Welcome to Section 1, Review, Filter Identification. Okay, so filter identification, let's first start off by thinking of the filters in terms of their outputs and a graphical analysis. Similar to a Bode plot, we're going to look at the characteristics graphically, and let's start with a low pass. So if the x-axis is frequency, so we've got frequency right here, and we've got 0 hertz right here, and frequency is increasing as it moves towards the right, and the y-axis is the right here, and it represents gain, some kind of gain or amplitude. Now a low pass filter, your low frequencies are what's going to get to the output, and the higher frequencies are going to be attenuated. So that's what a low pass filter waveform or frequency response would look like graphically. Okay, so now we're going to look at a high pass. Same thing, we've got 0 hertz right here. This is F, and we know that frequency is increasing as it goes left to right. We've got the y-axis is your gain or your amplitude. On a high pass, our low frequencies are going to be attenuated, and our high frequencies are going to make it to the output. I don't know why my drawing is not very smooth. Okay, good enough. Okay, band pass. Band pass, again, we've got 0 hertz here. This axis is frequency. Frequency is going increasing as we go left to right. We've got our gain or amplitude here. We've got on a band pass, we're only going to pass a specific set of frequencies. And so low frequencies are going to be attenuated, and then we're going to pass our pass band, and high frequencies are going to be attenuated. So there's our band pass. Right here is our band stop or notch, 0 hertz. Frequency increases left to right. Got our gain, amplitude, and our notch, our output is going to look like this. At lower frequency, we're going to have at the output, and then at a specific band of frequencies, we're going to be attenuated, and then our high frequencies are going to be at the output. So in this review quiz, we've got two reactive, basically 3 components, 2 reactive and 1 non-reactive. The capacitor and the inductor are reactive in that with changes of frequencies will affect their impedance, and the resistor, it just stays, the resistance is the same no matter what the frequency is. So for a capacitor, we know we have the formula x sub c is equal to 1 divided by 2 pi f c, frequency times capacitance. So we can see in that formula, as frequency increases, the x sub c goes down, it will decrease. So they've got with frequency and x sub c have an inverse relationship. For the inductor, we know that x sub l is equal to 2 pi FL. So frequency times the inductance in henries. With this formula, the inductance, we see that as frequency increases, the X of L increases. Okay, so when the inductor and the capacitor are essentially put together in the same circuit and in series, we know that these two are at resonance, frequency resonance. These two are of equal value, but they're also 180 degrees out of phase. So at resonance, an inductor in series with a capacitor, the equivalent resistance across both of them would be zero resistance. They cancel each other out at resonance. Okay, when the inductor and the capacitor, these two reactive components, are wired in parallel, at resonance, we get basically, the way I remember is the product over sum for the impedance. And the sum, the denominator part of that equation, is approaching zero. Remember, the capacitor and the inductor are 180 degrees out of phase. So as they become equal, they subtract from each other. So if your denominator is approaching zero, it doesn't really matter what's in your numerator. In this case, you'd have the product. But as the denominator approaches zero, your impedance of that tank will approach infinity. So at resonance, this circuit will have very, very high resistance. Okay, so now we've got a circuit, filter circuit, that we can see we've got two reactive components in there, and we can draw our graph. We know that at 0 hertz, we can see that the capacitor, X sub C for the capacitor, will be huge. So basically there'll be no circuit current. And if we think of the output as across the load or the resistor, we know that there's no circuit current, so across that resistor should be 0 volts. So we know at 0 hertz, we've got 0 volts. And let's imagine we're approaching infinity, like a really high frequency. We know that the capacitor reactance is going to be very, very close to zero, but the inductive reactance is going to be very, very close. It's going to be approaching infinity. So again, we're not going to have any circuit current. So the output is going to be 0 volts. Now at resonance, we know that X of C is going to be equal to X of L, but they're 180 degrees out of phase, so they'll essentially subtract from each other because they're in series, leaving us with zero resistance or impedance in that branch, which means that we'll have maximum circuit current and all of the voltage will be at the load. So we know we've got frequency resonance somewhere in here. We've got maximum voltage at that point. So we can see that our curve is going to be a band pass. Now, if that's a band pass, if we switch the location of the resistor and put the location of the resistor where the inductor and the capacitor are, and put the inductor and the capacitor still in series but across the output, you would essentially just flip the frequency response and you'd end up with a band stop. Okay, so here is a very similar circuit, but now the reactive components are in parallel. So we know that at low frequencies, so let's draw our curve. At low frequencies, the inductor is going to act like a short. So all of the, we're going to have a maximum current situation if the inductor is acting like a short, and we'll have all the voltage at the resistor, at the output. Okay, and at really, really high frequencies, so 0 hertz, frequency resonant, and approaching infinite. At high frequencies, the capacitor is going to start acting like a short. So it's essentially now all the current is going to flow through the capacitor and all the output voltage is going to be developed at the resistor. Now at resonance, those two in parallel, if you think of like the product over sum and the denominator approaching 0, we've got like we're approaching infinite resistance for that tank. So if that tank's in series with the output now, and it's a super high impedance, we're going to have minimum circuit current and no voltage at the output. So now if we connect this and we look at the response curve, we can see that this circuit is a notch or band stop. Now again, if we switch locations and we put the tank on the output and the resistor where the tank is, it would invert that response curve and we would have a band pass.